Hello everyone and welcome. My name is Dr.B the Chemie, and today I'm going to be talking about reverse engineering assessments, an alternative that you instructors can use in lieu of exams to assess what your students know. Now, as instructors, we often have an objective with our exams. There's two objectives in particular. So with our exam, we normally give students a problem and we tell them we want you to solve for a couple of unknown variables. So in this case, we're looking for solving M2 dot and M3 dot. And we're doing this so that we can understand students' mastery of course content. Now, with these exams and also with quizzes, there's another objective where we're also trying to understand any gaps in knowledge. I mean, you cover content for a few weeks in the class. You have an exam to assess what they know and to also identify what are the gaps in their knowledge. What do students not know that you would have liked them to have known? And so this is the objective of an exam. And you kind of experience, if you've been writing exams, there are some challenges with those exams, especially during a pandemic. So first of all, when you write an exam, one of the challenges is making sure that it's well aligned with all your course material, that your problems match everything you've been discussing in class. You didn't pick the one item that you discussed for 10 minutes at the end of one class, rather than something you've been spending 2 or 3 weeks discussing. Now, within those exam problems, you also are trying to write a problem that's going to challenge students. It's going to build on what you've been discussing in class, where your students have all the tools, and now you're going to reformat this question to get students to apply what they've known and apply it in a little bit of a different setting than what they're normally used to again see how well they've mastered this material. And so it's very challenging to write those kinds of problems that catch everything that you want and are at the appropriate level that you'd like. Additionally, when writing exams, another one of the challenges is timing and proctoring. You normally are constrained to a particular period of time to write for your exam to occur in, and you also have to proctor this exam, which can be a little bit cumbersome and take up a lot of time. Now, in addition to these aspects of exam writing, there's also some parts that we need to be concerned about from the student end, such as what do you do with students who are not good test takers? You have students that actively participate in class. They know the material, but exam day comes around and they freeze up. The recall is just, some students just don't have that quick of a recall on the information as other students. And in turn, they don't do well on the exam, even though they know everything. And so that leads us to question, are exams the best way to assess what students know? Additionally, there are times where some students are going to highly collaborate or sometimes cheat. And that's especially a problem and challenge online, where you have a lot less control over monitoring what students are up to, regardless of using proctoring software or telling students it's closed notes or using an honor system. It's very difficult to control any student collaboration and or cheating. And one of the other challenges with exams that starts from elementary school and kind of builds its way all the way up through college is that you start ingraining a mentality in students where they're fixated on there always being one right answer. And rather than students trying to learn and master a particular process in solving the problem, they're instead focused on, well, did I get the problem? Did I get it right? Is it right? Is it right, professor? Instead of, oh, okay, I understand the process. I can solve any problem. I did this, this, and this, like we've discussed, and the reasons that apply is because of this and this. So I'm very comfortable with my answer because of I know the steps. We would like our students to be comfortable with the process and confident that because of that process, they can get to the right answer, rather than, is this the right answer? And that's another one of the big challenges that comes about because we have given students so many exams, rather than focusing more on the process and not on the right answer. And so this is where REAs, or reverse engineering assessments, could be a wonderful place to integrate, or a wonderful thing we can integrate into the classroom as a substitute for exams. Now, I'm going to talk about what I did for one of my classes, which is a chemical engineering class, how I integrated it into my classroom, and what is the layout of an REA. And as my name, Dr. B the Chemie, hints at, I am a chemical engineer. So everything I'm going to be talking about is chemical engineering oriented. And so hopefully, if you are a chemie, you understand all the items I'm talking about. If you're not a chemie, welcome. I apologize for some of the terms that you may not be familiar with, but hopefully you still capture the essence of an REA. So for me, with my class, what I did when we had when the pandemic hit is that I had to change the structure of my class, and I was teaching material and energy balances, which some call Intro to Chemical Engineering. It's the first class that students take. And so for my class, what I did was something called a flipped classroom, where I prepared lecture videos for my students to watch in advance of class. Now, what goes along with those lecture videos is some homework assignments. Pretty much I ask some basic questions that students have to answer to demonstrate that they watched my video. There's no tricks with those questions. It's pretty much, did you watch the video or not? Because when students get into the class, we do something else. We work on in-class assignments, ICAs. And these are essentially regularly, they would be equivalent to homework problem sets that faculty normally will assign to students. And what I do with these ICAs is I get to spend class time going over our material with the students. Students get to practice everything. They get to talk to their classmates to make sure they're all going about the solution the right way. And then if the class or any particular students are stuck, they can ask questions to me or the classmates on what direction they need to go forward or how to go forward. And with my ICAs, I often like to give students what the final value is. Because I'm not grading by how well they complete the perfect solution. I'm grading primarily on effort. Did they try everything? Did they practice most of what we've been discussing? And a little bit is, okay, they got to the right answer. But for that reason, I don't care too much about them having, or I don't care that much about giving them the final value. Because I want them to go through it, and if they get the final value, they know I did it all correctly. And that's great. And so after we do a few of these ICAs in class, then it's time, we've practiced a lot of things, it's time for us to then do a reverse engineering assessment. And so with these reverse engineering assessments, there's two pieces that go into it. And again, like I said before, this is my substitute for an exam. So with an REA, the students have about 1 week, maybe 10 days to work on their reverse engineering assessment. And within that, they have to write their own problem and they have to solve it. Now, the reason I really like this is because a lot of students have been, they're used to the process of having an exam. They study a bunch of problems, they know the procedure, they know, okay, well, I'm just going to mimic this procedure and I should be able to get most of the question right or the whole question right. And so they no longer are challenged in working with the material. They just know the procedure. They can more or less plug and chug all these different problems or all these equations, and they come to the answers that they expect to get. Whereas in this kind of a situation, students no longer have that luxury. They no longer can just get a problem and solve it. They have to start from scratch. They have to write the problem and then solve it. And within doing this, they also have to make sure that this problem is solvable, that all the equations are going to work out. All the numbers are perfect. And because of this does require a little bit more effort on their end to make sure it's all going to work out and that they're using the right equations from the very beginning. And so that's the reason I really like these types of problems. And so for me, what I wanted to do is also go through one example REA problem that I assigned for my class for material and energy balances. Just to also give you an idea of how I've integrated within my prompt things to guide the students with writing their own problems, as well as ways to deter students from trying to just copy a problem that they might find in the textbook or online. And so for this prompt, I broke it up into pieces. So for the first piece, we got please write a material balance problem for a multi-unit process with at least 3 units. A mixing section counts as a unit, and at least 4 components, and solve for all unknowns by hand and with Excel. And by the way, that Excel is an amazing tool. For all the REA assignments, I generally have students do their solutions by hand and through Excel, because the Excel component is going to help me with double checking all the student work very quickly so that I can make sure that their math actually is going to work out. And so it simplifies my process of evaluating the student work later. So, okay, going back to this problem or the prompt, I gave this the first piece, and within this first part, I've already started to make some constraints or requirements for the students when writing their problem. And these constraints are that this material balance problem has at least 3 units, and there are 4 chemical species or components that they have to have within their system. Okay, and building off of that, the system must have a recycle stream. Only one stream leaving the system can be pure. And so again, I've added in a couple more constraints here. They have to have a recycle stream, and they can only have one stream being pure. And that one stream being pure is a really nice piece or requirement, because you could make this problem a lot simpler by just having every exiting stream be a pure stream. And I'm trying to prevent students from making those simple of a problem and challenging them to write something more complex and work through a lot more of their solutions. Okay, and then moving on within our prompt, we've got that the process should have at least 9 independent material balances. This problem should have exactly 0 degrees of freedom. And so for those who are familiar with material and energy balances, 0 degrees of freedom is the requirement. It needs to be 0, no ifs, ands, or buts. But we also, within my problem or my prompt, the students do have to write at least 9 material balances, which again is another constraint on the students. They have to put more effort or items within, they integrate more items within their problem. And then to wrap it all up, for their givens, they need to include at least 1 mass flow rate, 1 mass fraction, and 1 process specification that relates 2 streams and the amount of mass one has compared to the other. And so I've added, again, another couple of requirements for this problem. So if we look at cumulatively all the constraints I put on this problem, or not constraints, but requirements, there's a lot of pieces in here. And I'm doing that to ensure that students are going to be writing something authentic. Because each one of these requirements I include makes it that much harder for students to find a problem that they could try and present as their own. And instead, it makes a lot more sense for them to just write it themselves, because there's not going to be a lot of problems that are like what I just described. And if that wasn't enough to ensure that students are going to be authentic with their writing, I also have another piece to this, where I provide different chemical species that students could use when writing their problem. So for us, one example is they've got water, ethanol, glucose, and lactic acid. And when I give these chemical species, there's another motive as well with this. I'm trying to make these collection of chemical species into something that is relevant to industry. So for example, water, ethanol, glucose, and lactic acid are all relevant to fermentation. So any students that are interested in pharmaceuticals, this might be an interesting path to go forward with and look a little bit into the pharma industry to see how these components play a role, what they might be used for. Similarly, I also have a couple for air separation or gas separation. So we've got regular air and different components within air, such as your nitrogen, oxygen, carbon dioxide, and argon. And we've also got, if theoretically have noble gases all bunched together, how do you separating those out? And again, so if students are interested in the air separation process, they can look into cryogenic distillation, trying to understand that a little bit better. Because again, this is the first chemical engineering class for all students. So this is an opportunity for them to start getting a little bit more familiarity with the material and chemical engineering as a whole. So I think when I give these chemical species, it provides a double bonus of them getting familiarity with chemie. Plus, I know they have to be authentic with their problem. And finally, within these examples I've given, they've also got petrochemical production, so your alkanes plus water, carbon dioxide, oxygen. And then also, I thought as another fun one, we'd have a chemical synthesis set of chemicals for nitric acid production. So if there's students that are curious, how do you make nitric acid? They can look into that a little bit to understand the process and better help them when writing their problem statement. So as I said before, I strongly encourage as students write these problems to make sure that you have them do some computational form of it as well, such as an Excel spreadsheet, just so it's easier for you to track all the solutions for the students. So with this, there's the next step of evaluating this. How do we evaluate this? And I know it's a little bit more time consuming than if you were to write the exam. You have a solution set, you know, okay, all the students have to do this same step of set of equations to get the final answer. They lose this many points per step they miss. I recognize that the REAs are probably going to be a little bit more time consuming in terms of grading, but I think the benefits and challenge or the benefits in evaluating student knowledge and allowing students to write and be a lot more creative with their solutions outweighs the little bit of extra time it will take to grade these REAs. And so the way I break this down is I have 4 different criteria for the students where their problem statement is worth 25%. They have to draw a diagram and do a degree of freedom analysis. That's 10% of their grade. The solution's 45%, and the presentation is 20%. And when I say presentation, I mean as in the students write out the entire solution so that it's easy for me to follow. If it's hard for me to follow, I recognize that that's going to just take up a lot more time for me. And that's also doing the student a disservice because they will eventually need to write and articulate their ideas in an eloquent manner for when they go out to industry. So I thought that by grading presentation at this point would be beneficial for the students so that they start getting in the habit of writing well and documenting everything they're doing. And so I have these different criteria. I've given the point allocations, and then within each criteria, they can earn up to 100% of the points, and depending on the quality, they may earn less points. And so I've got different categories, such as an excellent category, a okay category, a what happened category. And so I fill in within my rubric what each category means. So for example, in the problem statement, if it's excellent, the student has written something that makes a lot of sense. This is physically possible, that can be done. All the numbers work out, and it's easy for me to understand what they were saying. And it matches with their diagram that they drew, which is another reason I have them draw the diagram, so I know that they match what they wrote. If they did an okay job, they've perhaps mixed and matched, saying they gave me a mass fraction, then called it a mole fraction later, or the numbers don't work out so that you have mass fractions that add up to over 1 or are under 1. And so for those kinds of pieces where it's kind of there but not quite, that would be an okay. And then what happened is that there's still quite a bit of mistakes going on, and this problem isn't really solvable, and I don't know what you're thinking. But I see that you've tried a little bit. And so you will have to use your discretion a little bit when grading these REAs, and it does take a little bit of time to acclimate and evaluating them. But again, once you get the rubric and you get in a group, it starts becoming a lot more efficient for you. And so with that, I wanted to also show, after doing this for 2 iterations, I've done it for 2 classes, that I've got some student testimonials. And this is unprompted student feedback. Students just wrote this in their surveys for the class about the REAs and how much they appreciated them. And so the first student wrote that they felt that they learned a lot by using the REAs in place of exams. They got to spend extra time making sure that they understood their concepts, and they got to produce their own problems and solutions. Another student felt that these REAs helped to see what goes into writing exam problems, and it helps with the fundamental understanding of the material, and they see how integral it is to writing problems. And the third student felt that REAs are effective, and they teach students the subject from a different and fresh perspective. So I did get a lot of positive feedback while doing these REAs, and I think students really appreciate that they do get extra time. They get a week or 10 days to work on these REAs, and that allows them to do a lot more to demonstrate what they know in comparison to an exam. And so with that, I wanted to wrap everything up just to highlight that these REAs, from what I've done, seem like a very effective means to substitute for an exam and assess what students know. Because students are challenged with writing their own problems and solving them, so they have to be a little bit more creative in this whole process. The students also have that even playing field. So good test takers, poor test takers, it's all the same for them now because everybody gets 7 to 10 days. And so they have an extensive amount of time to look through their notes and make their own piece of work with the REA. And finally, there's a lot of parts to your REA prompts that can deter cheating and ensure that your students have written something authentic. And so there's a lot, it seems like, so from my end, I would say I think there's a lot of benefit and upside to having the REAs and using that in lieu of an exam. And so with that, I wanted to say thanks a lot for tuning in. Greatly enjoyed your company for this REA discussion. And tune in for the next episode with Dr. B, the Chemie. I'll see you soon.